What if you could reduce your construction carbon emissions right now? Building materials are responsible for 11% of global carbon emissions, among which 19% accounts for the reinforcing bar's embodied carbon emissions in reinforced concrete structures. However, a sustainable solution already exists to change the future of our industry. STARS, splicing technology, allows reduction of steel. Thanks to its 35 years of pioneering experience in splicing systems, BARTEC Group has designed the Linction parallel threaded couplers, a very high-quality solution that allows to save 20% of rebars and their associated carbon emissions for an immediate positive impact on the environment. This splicing technology has already been used for many applications in international public and private construction projects, with top-level safety requirements, such as nuclear sites, bridges, government buildings, docks and sea foundations, stadiums, high-rise buildings, metro lines. On the railway extension Grand Paris project, 3,000 tons of steel were saved thanks to the Linction splicing systems. The number of trucks used in traditional overlap was consistently reduced. Thanks to STARS, the building sector can be brought in line with a net zero target sooner than expected. Come and join us to know more about this high-potential green building solution at STARS International Conference in Paris, October the 3rd.
Good morning, everyone, and welcome to STARS Conference in Paris. First of all, thank you for being here, to people who came here today, and welcome also to everyone who is connected online. First of all, I would like to say we made a little change in the plan because we have a lot of people connected online. We will do the whole presentation in one single take, so there will not be an interruption and the coffee break in the meantime, in the middle, but we will go from the start to the end of the presentation. So let's go into the subject first of all. STARS is a project that started at the beginning of this year, and it was introduced for the first time in Dubai on March 25th, 2022. At that occasion, the project was supported by the local Emirates GBC, Green Building Council, by the Institution of Structural Engineers, by CARES, which is the UK organization for certification of constructional steel, and by the Clean Energy Business Council. So today we are taking this project to Europe for the first time. So it is, I'm quite proud to be here in Paris because this is a new step for this successful project. So what is STARS and why are we here today? So the idea behind the project is that we are today facing an emergency for carbon footprint, but what is done is basically an assessment of the carbon footprint, trying to keep the total amount under a certain threshold. So this is basically what we see that it's done to face this emergency, whereas this project is trying to show that the issue can be faced since the beginning with a more efficient design in the design stage, because with an efficient design it is really possible to reduce what are the causes for the carbon emissions. So it is quite meaningful to be here in Paris today because it is in Paris where reinforced concrete started, because this guy, Joseph Monnier, he was a gardener from Paris, and in the half of the 19th century he had the need to try to give more strength to the pots that he was using for his gardening job. So his idea was to put into the material that for the pots he was doing some rods, some steel, and this is when he patented after this invention, which is seen today as the first example of reinforced concrete worldwide. So his idea was to make more durable flower pots. So durability, that this word we will see today, that is pretty much what we are trying to do again, and we will see during this presentation what can be done in this way. So after that invention, reinforcing bars were developed during the years, and these are some examples of today. So we went from different stages of the reinforcing bars, of the shape of the reinforcing bars. Reinforcing bars are obviously used to give some more strength to concrete. So what happens that concrete doesn't have really strength in tension. Concrete is pretty much designed for compression, and it's giving a very high performance in compression. But when it's tension, it's about 1/10 of the compression strength, and it is needed to add to the elements some reinforcing bars to make sure that it is possible to shape the elements according to the needs. So reinforcing bars can be considered the bones of the structure, and they can assemble. They are normally manufactured in steel mills, taken to the job site or taken to workshop that are preparing, cutting, bending the reinforcing bars that are then assembled in the job site and where the concrete elements are cast. So to do that, it is necessary because the manufacturing of this steel bars obviously comes into a certain specific length that is normally 12 meters. They need to be cut and shaped and assembled, and this job is done in the workshop. So it's from the steel mill, the reinforcing bars are going to the workshop, prepared, assembled, or taken to the job site, assembled into elements, and then the concrete is poured to create the element. So all this is obviously when you need to reassemble the bars, you need to join the reinforcing bars to create the cage. And to join the reinforcing bars, there are three possible ways. The first way, which is the traditional way that is probably used in 99.9% of the cases, is the overlap, which is it has been accepted in the last, since the beginning of the reinforced concrete structures, that the reinforcing bars can be put together over a certain length, and then that is the splicing between the bars. This length can be different. It can be 50 diameters normally, but could be even more for certain cases of design. As I said, it's you can see in any structures of reinforced concrete. This is the typical way of connection of reinforcing bars. Second possible method for splicing reinforcing bars is the welding, which has been used for a certain period of time, but is now not so much used because to achieve a performing connection of the reinforcing bars, you need a specialized operator. You would need also to check the quality of the welding with some methods that are not really practical on a job site. The third method of splicing reinforcing bars is with mechanical splice. Mechanical splice is existing since about 50 years, so it's not a brand new solution, and it is used in a lot of cases where mostly when the reinforcing bars are of a big size, the big size needs has a very long overlap length, and this is when mechanical splice becomes very efficient and very much used. Also, the fact that a mechanical splice can allow a lot of flexibility in the design is making it more and more popular in those areas where there is a lot of there are a lot of architectural ideas, new let's call adventurous design for futuristic structures, and Dubai is an example. Dubai is a place where design is really taken to the limit with very innovative and futuristic structures. And in this place, we can see a lot of need for mechanical splices, for solutions to connect reinforcing bars in a very efficient way. So mechanical splices, because they are very much used in the last 25-30 years. They needed to be ruled by norms. So there were some extensions of the construction norms where mechanical splices were included, and the rules have been developed. So today, this connection through mechanical splices is absolutely guaranteed, and is very well known, and it's used according to specific norms, international. There is ISO, there is American, there is UK, French. All norms pretty much all around the world. So let's check a little bit more about, let's talk a little bit more about the mechanical splices. Mechanical splice, what it is? Well, it is very, it's a very simple device that is designed to join two reinforcing bars, and it is designed to transfer the loads from one bar to the next bar. So this is the most, the easiest definition that we can give. And we can see a lot of different methods, because normally it's the two bars and the sleeve that is connecting the bars with a specific design for each manufacturer. The most used splicing system worldwide is certainly the parallel threaded splice coupler. But there are so many that is possible to find in the market that can be divided into two different families. Family with previous rebar preparation, meaning that the reinforcing bars that need to be connected need to be first prepared in the workshop or with specific machines that may be also placed on the job site. Is not. It is also possible that solution. So first the rebars are prepared and they are connected to the sleeve. So we can see here some examples of parallel thread or taper thread, or there are some grout threaded couplers, or in some cases some couplers with the upset edges of the bar. So these are all cases where you need specific machines to work on the reinforcing bars before the delivery to site. Second big family, which is the one without previous rebar preparation. You can see there is a largest number of couplers, but strangely enough, even if it's more populated, the family without rebar preparation, the most used couplers remain the ones in the first group, because having a system without the rebar preparation is including the fact that the sleeve, the coupler itself, needs to provide some kind of system to connect to the bar. So it's more engineered product, and it's normally more costly, bigger in size, or so for this reason it's much more efficient a system without with the previous rebar preparation. So during these years of history of the product, all solutions for applications have been developed. So we have all the couplers manufacturers develop their own solutions to respond to all those situations on the job site, to connect one reinforcing bar to the next. So there are some examples. Typical situation is the standard situation where the second bar can rotate and can be connected to the mechanical splice without any problems. But in some cases, you cannot rotate the second bar. Maybe you have two precast elements made of bars that cannot rotate, that need to be spliced. So there will be a solution that is called position coupler. Then other cases could be extension because of cages with different disposition of or replacement of the bars. And then you have special couplers that could be weldable for connecting to steel elements, anchors for replacing shaped bars at the end of the bar, for mixed use again for connecting to steel structures, for mixed structures, concrete and steel, and the transition when you need to pass from one side. Then there are also couplers made of different materials, could be epoxy coated, galvanized. So all the family of couplers that manufacturers of couplers could develop solutions for every situation that might happen on the job site to create some elements. So let's have a look to the typical projects where you can find mechanical couplers. I spoke before about Dubai because Dubai has a lot of high-rise buildings. High-rise buildings are one of the most typical projects because of the size of the bars. Most of the cases in the first floors are 40 millimeters, but also train metro stations. Nuclear power plants are really probably the biggest projects with mechanical splices. In some cases, the nuclear power plants, they are imposing to use the couplers for the construction of certain sections, docks, stadiums, big bridges. These are all the big projects that one could think about concrete with a massive usage of concrete are coming with mechanical splices. So let's go through a little bit more about the advantages of the mechanical splices. So before I was talking about mechanical splices versus the typical traditional overlap. We can say that the mechanical splices are not a real alternative to the traditional overlap, because they are bringing some extra advantages that the overlap is not capable to offer. So we'll go, first of all, we'll check the technical advantages. So talking about the overlap, the comparison with the traditional overlap. This is a column with an overlap, and where one can see very easily can imagine that once the concrete column is poured, the transition is guaranteed by the concrete, because the two reinforcing bars are not connected together, but just the embedment, the length of the overlap is accepted to be creating this connection. Once there is an issue of a design that is not done properly, there might be a situation like this. Without the surrounding concrete, there is no way that the two overlapped bars can stay connected together. So obviously, as I said, there are thousands and thousands of projects done with overlap, but the area of overlap needs to be protected with extra stirrups, with extra steel, and that has to be properly designed, not like this one, which is very, very poorly designed. But if we talk about mechanical splices, you don't need really to worry about the design, because a mechanical splice will guarantee that the transfer is going from one rebar to the next one through the device, through the mechanical splice, and like if the reinforcing bar was a continuous bar. So in case of failure of concrete, you can see from this picture, there is no the structure, the steel structure is not interested by the fact that the concrete is missing. So that's actually a very important feature, technical feature of mechanical splices, is to guarantee the continuity of the reinforcing bar without, even when the concrete is not there. So what does this mean? This means safety, obviously, because the fact that you have, as I said before, a bone inside the structure, you can also, as a designer, as a structural designer, you can also design the places where you want to, you want the structure to fail in case of accidents, so in case of earthquakes, so that these plastic hinges that have to be created by the in the structure can be easily designed also with mechanical couplers. Second technical advantage, going in order importance, so still talking about safety, it is a well-known and certified technology. Well-known because it's existing since 50 years, so there is no mystery about the fact that mechanical splices can offer a very good performance. And certified, why is certification is important? So first I want to thank again Gareth once again, who gave me the opportunity to help on this part as a certification body. Most of the projects I was mentioning before are public structures. All these projects, talking about high-rise buildings, bridges, or trains, metro, nuclear power plants, we're talking about projects where an accident would not be allowed. It would mean a lot of casualties. So it is extremely important to guarantee safety on these projects. And to do that, we have certification. Certification, there are rules talking about the performance of mechanical couplers, and there are organizations like independent bodies like CARES, like AFCAB in France, or ICC in US, that made a procedure that has to be followed to have a certification. This procedure is including full traceability of the product and marking of the product, quality control, so they will ask the manufacturer of mechanical splices to hold a quality control program, and random testing. So what these organizations do, they come doing regular audits to the manufacturing premises of couplers manufacturer. They take couplers, they do independent tests, and they check that what is designed corresponds with what is produced. So if we see, for example, the marking is telling the whole story of the coupler. What is on the marking, especially on the job site, where it's important to inspect what has been what is made by the contractor. It is always possible to check on every single certified coupler where it comes from, who is the manufacturer, what is the diameter, if the diameter is corresponding to the reinforcing bar where it is installed, and the batch number. Batch number will tell the story, will tell the day that the coupler was manufactured. On that batch number also is telling the story of the steel of the coupler, so it is possible to go and check the certificates, the material certificates of the coupler. So all the process of production is written on this little mark on every single coupler. So once certification is done, there are some certificates that are issued and kept actual every 6 months. They need to be they are updated. These certificates will give all the information about the approval of the product. So safety again. The result of all this process is that when a designer specifies a mechanical splice, a certified mechanical splices will deliver the performance that the designer is expecting. So in this way, the safety of the structure is granted. So other technical advantages using mechanical couplers will not create the need of having all this section where the reinforcing bars are overlapping. So basically you divide by 2 in the connection area, in the splicing area, you divide by 2 the number of the reinforcing bars, especially on big diameters. This is called congestion, and it will be an impact when it is too much reinforcing bars in the section. There is a major impact on the flow of the aggregates in the concrete element. So the fact that there is less steel, the element also in the area in the splicing area keeps the same properties as the rest of the element without changes. Another technical advantage, what is the idea behind the traditional overlap? What I said before, that the loads are transferred because of the surrounding concrete. We have to think that when we have mechanical splice, the load, the surrounding concrete is not considered when they are tested in the lab. This means that once they are casted into the concrete, there will be some extra strength provided by the surrounding concrete. The same concrete that was keeping the 2 overlapped bars together is also giving some extra strength to the bars that are spliced with a mechanical splice. Design flexibility, smaller sections. Again, the fact that you have less steel, you don't have to have all the double reinforcing bars in the element in the splicing area, will allow designers to keep the section smaller. Formwork saving. One of the typical applications of mechanical couplers is the construction in phases. So the fact that it is possible to interrupt the structure whenever needed is also allowing to preserve formworks to be drilled, to be prepared, and to be discarded after they have been used the one time. So this is pretty much the technical advantages of mechanical splices. Now let's go into the constructive advantages, where constructive is a more, let's say, practical area of usage of couplers. So with mechanical splices, it is possible to push a little further the design for prefabrication, meaning that it is possible to make prefabricated elements that are connected together through the mechanical splices. climbing formworks. It's a specific solution for high-rise buildings, and they wouldn't be possible without a system that is removing all the reinforcing bars that are coming out horizontally for the construction of the slabs in the second phase. So this is one very important. The walls, same is for diaphragm walls, top-down structures. They are one of the typical applications because of the advantages in terms of the practical advantage that they can provide. Another interesting point is the fact that when I will use an image to explain this. When, as I said before, reinforcing bars, the length the standard length is about 12 meters. So if we think, for example, a structure that is 60 meters high, if we consider, for this example, we consider reinforcing bars of 40 millimeters, every reinforcing bars will have an overlap length. 50 times 40 makes 2 meters of length. So this means that every bar, 2 meters are lost for the overlap. So 60 meters high, making things easy, would be 1, 2, 3, 4, 5 splices. So five times there will have to be a cast, the interruption of the structure with a new preparation for the next step of the column. When you use the the splicing systems, there is no loss in the length of each reinforcing bar. So there will be 1, 2, 3, 4 splices because the mechanical splices will allow to take these 2 meters down to nothing. So there will be one less step in the construction. This is obviously made with 40. It's not normal to have 40 millimeters bar in the after 50 meters height of a building, but that is to explain. That could be in a bridge, that could be in any elements, but basically each element, the fact that you can reduce the size of the overlap will automatically allow you to extend the length of the reinforcing bars that you have. With some advantages also for the waste, because if you have 5 phases compared to 4, you will add 20% more of system of bars that with the waste and everything else. So next constructive advantage of precast concrete elements is typical. It's not prefabricating the cages, but it's prefabricating the concrete elements that then are connected together on the site. There are mechanical splices that are designed to join to allow the connection of prefabricated concrete elements. Last but not least, the safety. In an ideal world, on the job site with mechanical couplers, you wouldn't see all these bars, all the reinforcing bars coming out of the structure, making the site much safer. So far, we've been talking about mechanical splices. All these advantages, technical, constructive, are very well known. It's a product that is existing since many years. Today, the idea behind the STARS project is to introduce a different point of view of mechanical splices, because besides these two technical and constructive advantages, mechanical splices can offer also a green advantage. And we are going to see what can be the potential for it and what can be and how this point of view that can work, can be faced. I was saying at the beginning of the presentation that we are facing an emergency today of the carbon emissions that need to be reduced at least of 30% by 2030. The steel is one of the biggest responsible for the CO2 emissions worldwide, because its impact has been calculated about around the 8%. All steel, not just related to the construction steel. With this situation, what can be done? Obviously, the obvious way, it would be to reduce the emissions coming from the production of steel, which is not so easy. All the steel manufacturers are working on that, but the fact that the process of steel is involving a lot of energy to warm up the ovens to make the steel. This energy is coming with a cost. One thing would be to reduce the emission coming from the steel, or the other possible thing that we can do now is to try to use less steel whenever possible. This is an immediate solution, because the time that it's going to be taken to find ways and means to reduce the emission of steel, there is a time span, but using less steel can be now, and this is what we are talking about today. Because so far mechanical splices have been seen just were never seen as a possible vehicle to reduce the amount of steel in the concrete elements. But the fact that if there could be less steel in there, less steel used would also mean a lot of different advantages, that reduction of emissions also on trucks, less trucks on the roads, energy for loading, unloading. So this would mean to have less steel in concrete elements. We will see how in a second. So this is only a first step that what we're taking today with the STARS project in this way, thinking that mechanical splices, and I said it already on purpose a few times, is a product that has about 50 years of history. So it's a very well-known product. We're not talking about something new that could be, no, it's a product we know very well. We know very well how it works. There are norms, there are certifications, it is safe. Never seen an accident with mechanical couplers, and all this make this product as a good candidate for helping in the way of, if this product is also green, that would be a perfect candidate, because we know that technically speaking it works very well. Let's talk a little bit more about the emissions and the CO2 impact. I will use two statements coming from International Energy Association, IEA, that, well, first of all, the buildings and building constructions, I will read it, combined are responsible for almost 1/3 of the total global final energy consumption, nearly 15% of direct CO2 emissions. So we're talking about, we were saying before, the steel 8%, but the building, with all goes together with the building, is about 15%. This was noticed, everybody knows it, and the IPCC is already, which is the panel of climate change, is already issued some policies, and these policies are asking designers to reduce the CO2 emissions from the earliest design stages. So this doesn't mean use products that that product has less emissions than the other product. It says try to reduce CO2 in the design stage. Find solutions where you have less CO2 emissions. So, and we have the solutions. We will see. This is a breakdown of embodied carbon in a building, where we see that almost 20% is coming from the steel reinforcing bars. This is supplied by the structural engineer, February 2021, and this is the breakdown for a finished building. So everything included after construction. 19% of emissions of embodied carbon is depending from steel reinforcing bars. So starting from this, we will see after what can be the impact on that from the solution with splicing systems. We will start now to we will go more into the meaty part of this presentation, just trying to understand the potential of mechanical splices facing this green emergency. Let's see, first of all, the weight, in terms of weight. So on one side, we consider according to the different diameters, we have from 16 to 40, the weight of the overlap of the solution with the overlap. And on the other side, we will compare it with the weight with the equivalent coupler that is connecting the two bars. So these are the couplers. So this is in kg, so it's 1.2 for the 40 and 80 grams for the 16. And we will see the equivalent reinforcing bars for the overlap would be this. So there is a huge difference. The more the diameters will go up, the bigger is the difference between the weight of the coupler and the weight of the steel. So you see, for the 40 millimeters, from 1 kg to 20 is 1/20 of the weight of the same for the 32, and so on. So this is already a good. This gives an idea already of what we are talking about in terms of steel. For each splicing, considering the building as thousands of splicing, each splicing there will be an equivalent, the mechanical splice compared to overlap is giving this quite impressive difference in weight, considering 50 times overlap. Let's try to see the impact of this on an actual project, and we are in Paris, so this is coming. It's next to Paris. We made a study based on the Grand Paris project, which is a railway extension all around Paris. So in this project, mechanical splices are very much used, but they cover just a little portion of not all the overlap have been replaced by mechanical splices, but just one part of it. But since it's a massive project, only for 2021, there were more than 300,000 couplers delivered to the job site. between 16 and 40 millimeters. So that the rest of this study will consider the range from 16 to 40 millimeters in terms of diameters of the reinforcing bars. So the idea was, okay, we know that more than 300,000 couplers were delivered to the project. The idea was to say how many tons of rebars were saved because couplers were used. We go and see it. So again, we consider only the weight of the total weight of the couplers of these 320,000 with a breakdown per diameter. This is in tons, and we see the total weight of equivalent steel that has not been used, but if it was used, this steel, we would have this. If we put all the data together, we have that 2,800 tons of steel were not used, but only 173 tons of steel were used. So we reduced, because couplers were used, there was a reduction of 2,600 tons of rebar, of steel. This is already impressive, but is coming not as a surprise, but let's try to understand what it means. It's not just removing the steel and having a saving in emissions of CO2. By the way, for this study, 185 tons of CO2 per tons were considered. Also for couplers, I mean, they have been put facing the same. But what is important is the fact, the percentage that 6% of CO2 or 6% of weight is when one solution with mechanical splice instead of overlap. But this is not the only advantage, because the fact that there are 2,600 less of steel on the site, it means that this steel never had to come to the site, and we have to think that steel goes onto trucks. 2,800 tons of rebars should be transported, and the trucks normally transport 20 tons per time. So we'll see that from the factory, from the steel mill to the steel fabricator to the workshop, from the workshop to the job site. Can be very far. It's not always next door, but this means that couplers, the weight of couplers, all the weight of couplers of these 320,000 couplers was loaded on 8 trucks, and the equivalent overlaps would be, take some time, because 108 trucks. So this means that there were saving steel in the structural elements, because using one solution rather than a different solution will have an impact, positive impact on things that one would not think in the first place, because all these trucks, they're not just the trucks need to be loaded, unloaded twice, and so there is no energy. There is also energy saving for loading, for unloading, and traffic around the Paris area is crazy. So removing all these trucks, and again, we are talking just about a little portion of the project. It's not all the So if one considers every day all the trucks with all the overlap going to the job site, is much more than that. So less trucks on the road means obviously less traffic, less time, energy, and greenhouse gases are obviously reduced. Again, this is 2021 Grand Paris. So starting from that, we we saw this, we made these calculations that were quite impressed about this, and we wanted to go a little bit further because it is a fact that mechanical splices are a green solution only after checking this compared to overlap. What we see that most of the bigger projects, they just use couplers, mechanical splices, only for a portion of and only for a limited amount of the application. Mechanical splices are a great technical solutions, and they are certainly superior to the overlap. We saw before all the technical advantages that they can bring. Certifications are guaranteeing the safety of the system, and but on we don't have to forget that because one will say, "But if everything is so good, why they are not used everywhere?" Because they are considered an expensive solution. So there is the designers believe that, and also the market make them believe that it is expensive to use a mechanical splice compared to the overlap. But we will see later a little bit more about the cost, because this is a very interesting point. Say this, we wanted to go a little further into our study, and we thought, what if the overlaps were replaced by mechanical splices? Because not just a limited amount, but we say, what if a structure was made only with mechanical splices? But first challenge is how many splices there are in a concrete structure, because it is not an information that is easily available. So we needed to make we needed to find a method to get to this information that is not available, because the number of splices will depend on the type of structure, on the norm that is used, on the steel grade, on the designer also, who has his own style of for designing the concrete elements, on the construction code, on the type of application. So there are a lot of variables. So it is extremely difficult to calculate before. Also, from the design to say it's the average is one splice every X amount of meters. So what the idea was to go upstream. So we just checking projects with couplers. For big diameters, 32 and 40 millimeter splices, they exist. There are some projects where the designers demand to put a mechanical splice on every single connection between the reinforcing bars, so no overlap allowed. So checking a few of these projects, we came up with this result that there is one splice every 6 meters of bar average. Just checking the existing projects, accomplished projects. The issue was from between 16 and 25. So to do that, the idea was to analyze the data coming from the people who are doing the cut and bending on the reinforcing bars. So it's at the very last step before the assembling of the bars. So checking all the logs, all the data on the machines to cut and bend the bars, thanks also to Ariadis, that gave us some support that made all this data available to us. We could make the stats of the actual cuts of the bars for a few projects. So a few projects were grouped, we worked together, and the cuts were clustered, so from less than 1.5 meters to 12 meters. So this is a typical breakdown of, there were a lot of projects grouped together that basically what this says is the 45% of the bars cut are between 2 and 5 meters. 5% is less than 1.5 meters, etc. So this is the distribution of the cuts of the bars in the project. We did make an assumption that we consider that not all the bars are spliced, that some that will not be spliced, 90%. And then we say that there is zero splice less than 1.5 meters, meaning that that is like scrap, not used for assembling cages. One each 4 meters, one each every 6 meters, and one every 10 meters. Then combining together with the quantities, I mean, this is not the subject of the day, but the curious thing that after all these data were analyzed and put together, again, in between 16 and 25 meters, it came, curiously enough, surprisingly enough, it came up that there is one splice every 6 meters of rebars. So once we have this information, we are capable to understand how many splices we can have in a structure. This is a very powerful tool because now with just based on the design and on the breakdown of the steel rebars that are needed for a project, we can say before how many splices we'll have in a quite accurate and still conservative way. So, for example, if we take this, we had a breakdown of an 18-story building that was about to start the construction. So, with very clear breakdown of the quantity of steel that are going to be used. So we converted all these quantities to splices, and we could compare. We say that we found that there are about 95,000 splices in this structure, and then we compare with couplers or with 50 meters, with 50 diameters overlap. And we see that when couplers are used, it's a 20% less of steel for building this 18-story building. Same exercise, two towers bridge, more tons because the size is more on the higher side. So 913 tons of steel, about 142,000 couplers, mechanical splices. So again, done with mechanical splices versus overlap, that would be minus 24% of steel if mechanical splices are used instead of overlap for the whole structure. So it means that every single splice after 16 millimeters, bigger than 16 millimeters, every single rebar is spliced with mechanical coupler. So this with the data, but when we have this tool that I said is very powerful, to know that you have average one splice every 6 meters of reinforcing bar, we can play a little more. We did this game, let's call it like that, in UAE, for projects in UAE that we connected, that we know quite well. So, because one of the first objections to this project was, yeah, but in UAE, in Dubai, I got this objection from someone from the government to say to me, yeah, but here in UAE, everybody uses couplers already, so what are you coming to tell? We already use it. I say, fine, let's see. Let's take some projects that use couplers, as they say. So as made, we have this project like the Bloom Towers. It is in Dubai. They used 64,000 couplers. It's a large quantity of couplers for a project here in Europe. You say, wow, this is a lot of couplers used, but we know the breakdown of the steel that was used for this structure. So we know that the couplers were used only for a little portion. So 6% was saved because they used couplers. Fine. Let's see if they used the couplers for the whole project instead of a small portion. There would be 464,000 couplers, very large quantity, 18% saving. So it's true, they already use couplers. They save already steel because of couplers, but they can save 18% and not just 6%. We make the same exercise for a couple of more projects. So for example, this is a mall, has made 32,000 couplers, 4% still saving. We made the calculation, 380,000 couplers, splices, so we put couplers, we compare with the overlap, and 20% could have been the saving if all splices were used. Same for the, we checked another project. In this case, only 5,000 couplers were used. Yes, they already used couplers, fine. But with, if all splices were done with mechanical splices, there would have been an 18% saving of steel in this project. So we have already some conclusions that we can come to conclusion that we can say at this point. It is a very well-known technology and certified. It's bringing more safety. There are technical benefits. There are constructive benefits, all that I said before. So, and the conclusion is that it is quite obvious that the more mechanical splices are used, the more steel is saved, and the less emissions that we would have. So at this point, that would be great if this could be done. But the question that comes is at what cost this can be done. So, because solution is great under all points of view, but if this solution is not sustainable under the economic point of view, there's no point in it, as it's too expensive. So let's go and check the costs, and again we will compare again the overlap with the mechanical splices and under the cost point of view. And again, we take Dubai as an example. And why do we take Dubai as an example? Because Dubai is a place where mechanical splices are very much used. So it is meaningful to consider a place where the product is already used and everybody's equipped to supply one supplier or the other. And but because this has brought the cost of the mechanical splice as like one of the existing constructive solutions. So it's not just like a specific, just in case solution, like it is more here in Europe still now. But it's a place where mechanical splices are very much used. So the cost of mechanical splices went down, and we have a breakdown here of overlap compared to mechanical splice, where we can see that this is end of March comparison, where we can see that for after 32 millimeters, 25 is pretty much the same, the cost, and after 32 millimeters, the cost of actually is the other way around. The cost of the mechanical splice is this part, is 9, is turned the other way around. The mechanical splice will be higher in the small diameters, but the more the diameter goes up, the more the cost is going down compared to the overlap for mechanical splices. So Actually, this is the overlap and mechanical splices are audio have been switched. So this will tell us with a big difference on the big diameter. So this makes 32 millimeters and 40 millimeters much more effective in terms of cost for the big for the big diameters. But these costs are compared between the mechanical splice, the market cost of mechanical splice compared to the steel, just to the steel, to the cost of the steel multiplied by the market cost of the steel. There's nothing else. But let's see what is the overlap, because it is not correct. We believe it's not correct to compare the mechanical splice to the cost of the reinforcing bar without considering a lot more factors that should be added to the cost of the overlap, like the fact that there is a steel rod that ties together the rebars, that there are some, I showed before the picture of the column failure in the column, and I said it's not a good design because there are not enough stirrups, because the sections with the overlap needs to be protected by extra stirrups. So there is more steel that is needed to add to that area. There is we consider all the time 50 diameters for material cost, but it could be more than 50 diameters in some cases. In some areas they ask for 60 diameters, so this is 70 in some seismic areas as well. So this can be higher. Overlaps, rebars and tracks, loading and unloading. The more rebars you have, the more of these operations you have to do. So the more costly is to it's an extra cost that should be considered as well to add on the top. Overlap, we can also say it's not a certified splice, so it's something that should be considered, that we are not exactly comparing the same things. There are also hidden costs, because once the overlap is installed, there is extra formwork preparation, congestion, all the consequences of these disadvantages of overlaps that we mentioned before will be converted to extra costs that were never considered when comparing one solution to the other. Longer operation, again, for congestion. In some cases, climbing formworks can be used only with mechanical splices. If you don't use that, you need to do an high-rise building with reinforcing bars. It will take days and sometimes more months to make the same structure. The cost of steel can change, can go up, can go down, but it can go up during the project execution. It's not under control and on the day one on the job site. So the price is variable. It's not exactly possible to know. Nobody can tell beforehand how much is costing an overlap. So whereas mechanical splice, it comes, it's very easy. It comes, it's a rebar preparation plus the cost of the sleeve. There are market prices for the splicing. It's not even discussed. This is how much is for that. The cost is clear. So when you have threaded coupler, it will be one coupler plus 2 threads, and that's it. So we do not see any hidden cost after that could have an impact on the price on the coupler that should be considered. So at the end, the price for the end user is fixed. So we have fixed price against variable price. talking about costs, applying the same costs that we saw before to existing projects. Let's see what would be the impact of these prices on existing projects. I left the currency in AD because that was easier to leave it like that. But what is interesting is that if this building was done with all those couplers that we said before, only with couplers, the cost increase would have been 0.5%. With a saving of 18% of carbon. I'll work them all, same process as before. Cost increase, if it was done completely entirely with mechanical splices, would have been 0.7% more costly, the whole project. Still saving 20%. And this is waterfront development cost increase 0.4%, upfront a saving of a footprint of 18%. So this is quite impressive to see that the specifying all mechanical splices, the impact, the cost impact on the whole structure, as we see, as we calculated on existing and the actual projects, is less than 0.7. When we have, as we saw, a reduction of footprint, which is always higher than 17-18%. This difference could go even down to 0 because it's a small percentage after an extra diffusion, if the market was completely converted to mechanical splices, the market price would go certainly down. So this cost is a top difference that we can have today. So the impact is so I've upfront a more close to 0 increase of cost. So we have an impact on the environment which is higher than 18%. And what does this mean? We take again this breakdown in the structure before that we saw before, where we saw the reinforcing bars were representing about a 19% of the impact of the embodied carbon. If we see that if we use mechanical splices, we have an impact of higher than 18%, and the 18% of 19% would be higher than 3%, which is an impact that is coming just using a product that is existing and that can be specified in the design stage. So there's nothing, with all the advantages that we have been seeing up to now. So what are the conclusions? That we saw the organization, what they say, they ask to find means to reduce emissions and increase safety and durability. And this durability is the same durability that was looking for this guy, Joseph Monnier, when he started with the reinforced concrete. So the conclusion of all this is that the immediate solution is there. There is an immediate contribution that can come from the fact that mechanical splices are used. The smaller the better, because all what we have been saying today is that has been calculated with the small sized couplers, because there are all sizes, so there are also big sizes, but the most popular couplers are of a small size. This is an immediate solution for the emergency, and they could be a solution just specifying in every project the mechanical splices. There is a direct, straight impact of reduction of carbon footprint. So this is pretty much STARS. What STARS is, the splicing technology allows reduction of steel. The project was developed from BARTEC Group, from BARTEC Company, which is manufacturer of a splicing system. I believe that, Karine, on va faire partir la vidéo après? After this, the conclusion of this presentation, there will be a short video introducing the company, which is active since more than 30 years to manufacture, to design and manufacture splicing solutions. Today we are very much into this subject of green, trying to find a green contribution, a green solution for improving our environment and to respond to this emergency that is affecting us all. So I would like to thank everyone who participated. I don't know if we have any. Okay, so we'll stay online. That will be the small video. Thank you very much, and have a nice day. Thank you.
BARTEC Company is a French worldwide leader of certified quality splicing systems. Let's have a closer look on BARTEC Company, its history, its mission, success, and future planned developments. BARTEC Company is a specialist of splicing systems for reinforcement bars, realized by connecting parallel threaded couplers to rebars, threaded with machines specifically designed and built by BARTEC Group in its Italian premises. BARTEC Company has 30 years of successful history and experience, and a team of engineers specialized in creating high-end technical solutions to be delivered to major concrete projects like metro lines, stadiums, bridges and viaducts, high-rise buildings, power plants, most of them public structures where a failure is not admissible. More than 10,000 structures were realized with its original technology without reported incidents. The activity of BARTEC Company started in 1988 with its original design and introduction of the first parallel threaded splicing solution, realized through the combination of a parallel threaded couplers and rebars, threaded through a 3-steps operation of cutting, cold forging, and threading. The process as it was designed was assuring top capacity in the threading production process and top mechanical performance of the installed couplers, with a consistent tensile failure happening remote from the splicing area. BARTEC patent was an immediate success, and in order to supply all job sites requiring it, BARTEC Company chose the strategy to license 2 external companies to support its distribution outside Europe. By multiplying its commercial efforts in this way, what was soon called the BARTEC system became very quickly the most used splicing system in the world, replacing the traditional overlap splicing or previous expensive and inefficient splicing solutions. In 2008, BARTEC patent went to public domain, and several companies, mostly Asian, started to manufacture similar products, focusing on low cost rather than quality. BARTEC Company continued focusing on R&D to improve and provide high quality and certified solutions to ultimately guarantee safety to the structures. In 2012, a French industrial group, which later became BARTEC Group, incorporated BARTEC Company, together with the Italian company Sergel, manufacturer of threading equipment, with the idea of relaunching BARTEC Company as a global supplier. It is thanks to this renewed strategy and in line with its tradition of pragmatic innovation that BARTEC Company could launch in 2013 its brand new, exclusive patent for a parallel splicing system called Linxion Pi. Today, the top performing splicing solution of its kind in the market. This was another milestone in the BARTEC company path, already populated with new technical solutions and patents. As a matter of fact, the mission of BARTEC company is to build a strategic partnership with its customers, as BARTEC company believes that in the present market situation, only a serious technical approach and flexibility can bring the right solution to job sites that are becoming more and more challenging in their request of cost-saving and high-quality performing solutions. BARTEC company results are exceptional. Within only 4 years, its turnover has doubled. 2 branches started in UAE and China. Linxion was approved and used in nuclear projects. New distributors were found, covering a lot of international markets, and the growing trend does not stop. BARTEC company, pragmatic innovation.